minus 2x plus 5. And so our first derivative, which was just our derivative before, I'm going to use the power rule on each of these terms. So we have 3x squared minus 2 plus 0. And if I want to talk about the derivative of this function, well, I'm going to be calculating f double prime of x. And so again, I'm going to be applying my derivative rules. So I'll bring that 2 down in front, so I'll have 6x minus 0. So there is our second derivative. F double prime is equal to 6x. Our third derivative will be 6. And our fourth derivative of a constant, is 0. And from now on, our fifth derivative of 0 is 0. So any derivative that is the nth derivative where n is greater than or equal to 4, that derivative is equal to 0 on this example. So on this particular answer, on this particular derivative, on this particular function, once we get to a certain point, our derivative goes to 0. Okay.
But you're saying they don't all work that way.
Nope. Let's look at another example. All right, so here's one. We've got f of x is equal to 2 times the cosine of x. Now, our first derivative, I've got a constant in front, but it's multiplied by something that's changing, so that means that I'm going to carry along the 2 and take the derivative of cosine of x. What's the derivative of cosine x? Yeah, negative sine x. So our first derivative is negative 2 sine x. Our second derivative, I've got a negative 2 in the front, and then derivative of sine x is cosine x. And now I can take my third derivative, and so I've got negative 2 times the derivative of cosine x. Derivative of cosine x is negative sine, so the negatives cancel, and I've got 2 times the sine of x, okay? And then we've got our fourth derivative, which is 2 cosine x.
This is what I thought when you were saying all of the different ones. I was like, wouldn't you just go into a circle back to f? To the original?
So one type of function, polynomial functions, keep taking derivatives, eventually you're going to go to 0. With this example of a trig function, we end up going in a circle because now here our fourth derivative is exactly the same as our... Now, this first one, we would kind of think of this as the 0th derivative, if you want to say. The original function is no derivatives at all. And so our fourth derivative is exactly the same as our original function. And so that means that's going to continue going around in a circle, and so you can keep doing this, and you could calculate the 257th derivative of our function, if you wanted to. So I'll let you think about that one. All right, so think about that one, and maybe we can come back to it. And so it's cool. Some of the derivatives go to 0 as we continue to repeatedly take derivatives. Some will go in a cycle, and what you'll find is that some of them are going to blow up in your face. So, for example, think of tangent, or think of secant. Derivative of secant is tangent x, secant x. Next derivative involves the product rule. Boom. Now you've got a lot of stuff to work with. So these derivatives can start to blow up in your face, get bigger and bigger and bigger and more complicated. Or they can get easier and easier and easier and less complicated. Depends on the type of function. Okay, so I'd like to wrap up with our last 5 minutes by talking about an application or a reason why we would care about these higher derivatives. All right, so an application. If we have a function that we call s of t, if that function describes position at time t, okay, position of an object at time t, then s prime of t, the derivative, is describing instantaneous rate of change of position, which is velocity. So s prime of t is velocity of the object. So the original one is position of the object. S prime is the velocity of the object. And so we might say that s prime of t is velocity, v of t. If we take the derivative of velocity, we have s double prime, instantaneous rate of change of velocity, that's going to be acceleration. So s double prime is the acceleration of an object. And so s double prime of t, well, that's the first derivative of velocity, so that's v prime, and that is our acceleration, a of t. All right, so if you start out with a position function, your first derivative is velocity, your second derivative is acceleration. And if we want to keep going, we can take a third derivative. The third derivative of position, anybody know what that one's called?
Rate of change of acceleration.
Okay, instantaneous rate of change of acceleration. True. Anybody else know what it's called?
Is it jerk?
Yeah, that's jerk. Okay, so s triple prime is jerk. The jerk of an object. All right, so s triple prime is the same as the second derivative of velocity, which is the first derivative of acceleration, and we call that j of t. Now, in a typical free-falling world where the only acceleration that we have is gravity, gravity is constant, 9.8 meters per second squared, so jerk is 0. So in our standard world, unless we are adding extra acceleration into our system, then we don't really think about jerk too much because jerk is 0. Okay, any questions or comments about that? All right, in that case, we should wrap up here so we have time to go over to the computer lab.